As we have stated in our previous discussion, one example or the most important example for motion with constant acceleration are your freely falling bodies. In the 4th century BC, Aristotle taught that heavy bodies fall faster than light bodies in proportion to their weight. So Aristotle thought that heavier bodies should fall faster as compared to the lighter ones. For example, if you have a feather and a stone and you drop the feather and the stone at the same instant, you will see that the stone will fall faster compared to your feather. Your feather will slowly fall down. And that is also what Aristotle taught. However, 19 centuries later, Galileo argued that a body should fall with a downward acceleration that is constant and independent of its weight. So Galileo does not approve or does not agree with what Aristotle taught. So again, Aristotle taught that heavy bodies fall faster than light ones, but Galileo showed that all bodies should fall at the same rate, regardless of what their um, weight or what their masses are. Now, what is the problem with the idea of Aristotle? In the idea of Aristotle, you have your air resistance. However, according to Galileo, if there is no air resistance, like let's say let us drop the feather and the stone at the vacuum, the downward acceleration of any freely falling object is equal to the acceleration due to gravity, which is equal to 9.8 meters per second squared, or this is equal to 32 feet per second squared. So the body should fall freely at the constant acceleration due to the acceleration of gravity, which is again equal to 9.8 meters per second squared. Thus, Aristotle was wrong. What are freely falling bodies? When we say free fall, this is the motion of an object under the influence of only gravity. Again, for your freely falling bodies, we disregard the effects of air resistance. In the figure shown, a strobe light flashes with equal time intervals between flashes. So you have a camera set up and then you drop a clear bulb and the flash will uh, take take photographs at equal time intervals, let's say at every 1 second. And as you can observe, at every 1 second, the displacement of the ball is not the same. The ball's displacement increases. The velocity change is the same in each time interval, so the acceleration is constant. What happens with with the ball is that the ball is accelerating due to the acceleration of gravity, acceleration due to gravity, which is equal to 9.80 meters per second squared. So these are our assumptions for the acceleration of free fall. Again, we neglect the air resistance. Second, free fall motion is constantly accelerated motion in one dimension, which is along the vertical axis or your y-axis. And we let upward be positive. So you have your positive y and then your positive or your negative y downwards. And we use in the kinematic equations your ay is equal to your negative g, which is equal to negative 9.18 meters per second squared. Again, it is a negative because the acceleration due to gravity is downwards. Okay, and we have here your negative y-axis. So you have your negative g of negative 9.18 meters per second squared. Please take note of that one. That again, for upward, it is positive, and for downwards, it is negative. Let us take a look at your four equations of motion for constant acceleration again. So here, you have your four equations for constant acceleration under in the horizontal motion. This is your equation 1, your equation 2, your equation 3, and then your equation 4. We can still use the same equation for motion along the vertical axis. This time, you have your Vy is equal to your V naught y plus Ayt. But previously, we have stated that your Ay is equal to the negative g. So we replace all the Ays with negative g. Thus, we have your Vy is equal to V naught y minus gt. Your second equation, you have your y minus y naught is equal to V naught yt plus 1 half Ayt squared, placing Ay with negative g. You have your y minus y naught is equal to V naught yt minus 1 half gt squared, and so on and so forth. So these are your four equations of motion for vertical motion. Again here, when we have the sub x in your equations, we're referring to your horizontal motion. When you have your sub y's, we're referring to your vertical motion. Please do not confuse these equations. Let us have an example. This is a freely falling coin. A 1-year coin is dropped from the Leaning Tower of Pisa and falls freely from rest. What are its position and velocity after 1 second, 2 seconds, and 3 seconds later? In this problem, it is stated that the coin falls freely from rest. So this is a free fall problem. We are given with your Ay is equal to negative g, as it is a free fall, and your initial velocity, since it is dropped from rest, you have your V naught y is equal to 0. If we consider the point where we drop the coin as your origin, let's say that is at y equals 0, everything upward is positive, everything downwards behind this point is your negative y. So if that is the case, you have your y naught, where we drop the coin, to be at y equals 0. Our target are the position and velocity. So that is y and by. You can look into your four equations of motion to see which of the equations we can use to solve for the velocity and the position. For your position, we can use equation 2, and for the velocity, we can use equation 1. Solving for the position, you have your y minus y naught is equal to v naught yt minus 1 half gt squared. Your y naught is just 0, your v naught y is 0, so this term goes to 0. So your y is equal to minus 1 half gt squared, or this is equal to negative 1 half times 9.80 meters per second squared t squared, or your y is equal to negative 4.9 meters per second squared t squared. For your velocity, you have your Vy is equal to V naught y. You have V naught y minus gt. But your V naught y is 0, so you have your Vy is equal to negative gt, or this is equal to negative 9.80 meters per second times t. At time equals 1 second, you can get a y of equal to negative 4.9 meters, and your Vy is equal to negative 9.80 meters per second squared. Negative 4.9 because your coin moves downwards, and negative g because, again, it moves downwards. If it was positive, that means your coin moves upward. But we have here a negative y and negative Vy. You can solve the problem for a time 2 seconds and 3 seconds, and I will leave it to you as your assignment. Let us have another example on free fall motion. This is an up and down motion in free fall. You throw a ball vertically upward from the roof of a 24-meter tall building with a speed of 15 meters per second. So in this problem, you are giving the ball an initial velocity of 15 meters per second by throwing it upwards. On its way back down, it just misses the railing. So we can see the problem like this. You throw the ball upwards, and then of course it goes downwards because of gravity. And as it moves downwards, it just misses the railing. The problems are: find the ball's position and velocity 1 and 4 seconds after leaving your hand. B. The ball's velocity when it is 5 meters above the railing. C. The maximum height reached. And D. Its acceleration at the maximum height. Let us solve this problem one by one. Again, you throw a ball vertically upward from the roof of a 24-meter tall building with a speed of 15 meters per second. This problem, you're given with an initial velocity v naught y, which is a positive because you throw the ball upwards of 15 meters per second. Okay, our target is to find the ball's position and velocity 1 and 4 seconds later after leaving your hand. So we are given with times 1 second and times 4 seconds. 4 seconds. Sorry. Time 4 seconds. Okay. Our target are the ball's position and velocity. So we have your y and your vy at times 1 second and 4 seconds. Solving for y, you can use your equation number 2 like we did in the previous example. And you can use equation 1 to solve for vy. Solving for y, we have y minus y naught. This is equal to v naught y, v minus 1 half gt squared. If we consider the point at the railing where we throw the ball to be at your y equals 0, okay, consider that one as your origin. We take your y naught equals 0. Again, this is the point where uh, you throw the ball upwards. So this is 0. In your y is equal to 15 meters per second times t minus 1 half times 9.8 meters per second squared t squared. For your velocity, we have v is equal to your vy is equal to your v naught y, okay, minus gt. So your v naught y is equal to 15 meters per second minus 9.80 meters per second squared times t. We're going to use this expression to solve for at time equals 1 second. And you can find that at time equals 1 second, your y is equal to a positive 10.1 meters and your vy is equal to positive 5.2 meters per second. Meaning at 1 second, your ball still moves upward. And you'll see that at time equals 4 seconds. Using the same expressions, you'll find your y to be equal to negative 18.4 meters and your vy is equal to negative 24.2 meters per second. You get negative y and vy, so that means this is now downwards from your railing. So downward. Okay. Now, as you can see here, the velocity of your ball at 1 second is only 5.2 meters per second, which is a lot smaller compared to the initial velocity, which is 15 meters per second. So as you can see, when your ball travels upward, it slows down and then it reaches the maximum height. And as it reaches the maximum height, it goes down again, accelerating at 9.8 meters per second squared, which you can see in the magnitude of your Vy at 4 seconds. It is now greater at 24.2 meters per second, greater than 15, meaning your ball is accelerating downwards. Okay, and it moves downwards. You have your negative 24.2 meters per second. For problem B, we are asked for the ball's velocity when it is 5 meters above the railing. For this problem, our target is the ball's velocity By given your y is equal to 5.0 meters above the railing. Again, you have your y naught is equal to 0. This is at the railing. Okay, our target is your Vy. You still have your given V naught y equal to 15 meters per second. Okay, and you can look at which of the four equations we're going to use to solve the problem. So our target is your y. Of course, we cannot use equation 1. We do not have the y terms here. For equation 2, we do not know the time, so we cannot use this one. For equation 3, as you can see, we can use this one. You have your g, you have your y terms, and you have also your v naught y, and then the term you're looking for, which is your vy. Equation 4, we cannot use this one because we do not know the time t. So we use equation number 3. So let's solve the problem. You have your negative 2g y minus y naught. This is equal to Vy squared minus V naught y squared. Our target is your Vy. So moving terms, you have your V naught y squared minus 2g y minus y naught is equal to Vy squared. Okay, this is just 0 here. So you have V naught y squared minus 2gy is equal to Vy squared. Your Vy is equal to the square root of V naught y squared minus 2gy. However, if you can remember from your math, the square root has two roots. You have a positive root and a negative root. So let's continue solving the problem. You have your Vy squared is equal to, you have 15 meters per second squared, okay, plus 2, 9.80 meters per second squared times 5 meters, which is your y. So you get a Vy of 127 meters squared per second squared. Take note here that your meters here is squared, your seconds here is squared. You have meter times meter, so you have meter squared over second squared. So your Vy then is just the square root of this one, so you have positive negative 11.3 meters per second. What does positive negative 11.3 seconds mean? So when we say positive 11.3 meters, as you have observed, when the ball goes upward, if this is, say, for example, your railing, if the ball goes upward, okay, 5 meters, say, for example, this is the 5 meters here, it goes upward, reaches 5 meters. So this is the positive 11.3 meters. When it goes downwards, it passes again 5 meters above the railing, this point here. Okay, so when it goes back downwards, you have your negative 11.3 meters per second velocity. Okay, so the positive is when it goes upward, and the negative is when it goes downward. Again, this is here the path of the ball. So those are your positive and negative 11.3 meters. Positive for going upward and negative for going downwards. Let's solve problem C. Find the maximum height reached. So we're asked for the maximum height reached by the ball. So what happens with this problem is that if you try to imagine throwing a ball, so your ball goes upwards, and then you will see that there is some maximum height that the ball will just suddenly stop, right? And once that maximum height is reached, the ball will go downwards, okay? Following again a straight path. So the ball will just go up and then just goes down. Again, straight path. On the previous slide, I've drawn something like this, okay? But this is not the actual path that the ball has traveled. This is just to let you see your up and down motion. But in reality, or in the problem, just to make it clear, the ball goes upward and the ball goes downwards, following the same or along a straight line. Okay, and there is this maximum height that the ball reaches, okay, where the ball suddenly stops and then it goes back downwards. So let us solve this problem. Let's find that maximum height. Okay, so the maximum height reach is our target. So our target is your y. So here, since it reaches a maximum height, and then um, imagining that you throw the ball at maximum height, you know that the velocity of the ball is 0, right? Because it stopped at the maximum height. We still have your initial velocity equal to 15 meters. Okay. Then you have your y naught at the railing, be 0, because we considered it again as r origin. So let us solve the problem. We're looking for y. Let us look at your 4 equations of motion. Can we use equation 1? No, because you have the time term. So this is not usable, of course, with equation 3 or equation 2, and then, of course, equation 4. We cannot use this one. So we can only use your equation 2. So let us solve the problem. So you have negative 2g y minus y naught is equal to vy squared minus v naught y squared. Your vy is just 0 because at the maximum height it stops. Your y naught is 0. So you have negative 2g y. This is equal to negative v naught y squared. We divide by negative 1 to remove the negative. So you have 2g y. This is equal to v naught y squared. We wanted your y. So divide this one by 2g. This cancels. Divide by 2g. So your y is equal to v naught y squared over 2g. This is 15 meters per second squared divided by 2 times 9.80 meters per second squared. Okay, so the meter cancels, or the one of the meter cancels, and your seconds cancel. So you have your y is equal to 11.5 meters. So this is the maximum height reached. For our last problem, letter D, what is the acceleration at that maximum height? This is actually a direct question. At the maximum height, we still have the acceleration is equal to 9.80 meters per second, or negative 9.80 meters per second squared, because it is under the constant, or it is under the influence, still under the constant influence of the acceleration due to gravity. If there was no acceleration at the top, at the maximum height, the ball would just stay there forever, right? But since the ball goes downwards, that means it is still under the influence of gravity. Now let's review what we have learned so far. In this lesson, we have started our discussion on mechanics, starting with kinematics. We have learned the concepts of reference frames, the displacement, the velocity, and acceleration. We have also discussed motions with constant acceleration along the horizontal motion, and the most important example of your motion with constant acceleration, which are your freely falling bodies. That's it for this lesson. See you in the next videos. Thank you.